Let us look at the concept of centralizer and normalizer. The centralizer of an element A in G is the set of elements that commute with it. This is written as, for A in G, centralizer of A in G is equal to the set of elements in G, where G times A is equal to A times G. Remember, this can also be written as G times A times G inverse equal to A. Now, that was with respect to a particular element. Now, with respect to a subgroup, we can also say centralizer of a subgroup is a set of elements in G that commutes with each element in the subgroup. So this is basically an extension of this to a subgroup. And this is written as centralizer of the subgroup H in G is equal to the set of elements in G, where G times H is equal to H times G for all H in the subgroup H. Okay, so that was centralizer of an element and centralizer of a subgroup. Now let's look at some properties. Here, if we take E as A, then centralizer of A in G is equal to G. What does this mean? It means since every element of G commutes with the identity, that means the entire group is the centralizer of the identity element in G. If G is a abelian group, then pretty straightforward, you know that every element of an abelian group is commutative with every other element. So that means again the centralizer of A in G is equal to G. Centralizer of A in G is a subgroup. So that means the set of elements that commute with a particular element, that set forms a subgroup. The order of the conjugacy class of A in G is equal to the index of the centralizer of A in G, which we call the index. Remember, we saw that previously. If H is the subgroup generated by an element A, then the centralizer of that subgroup in G is equal to the centralizer of A in G. H is equal to G if and only if the centralizer of the subgroup H in G is equal to the center of G. Now, if the centralizer of the subgroup H in G is equal to G, then H is a subset of the center of G. Now, let's look at an example. So here, S3 is the group that we have taken. And which all elements of S3 will commute with E? All of them. So that means S3 is a centralizer of A in G. Here A is E. Now, if we take the permutation 1, 2, then the centralizer of permutation 1, 2 in G is E and permutation 1, 2. Similarly, for 1, 3, it is E and 1, 3. For 2, 3, it is E and 2, 3. Similarly for these two. Okay, now let's look at the normalizer. Normalizer is a set of group elements that conjugate the entire subgroup back into itself. So this is written like this: normalizer of H in G. Remember, this is with respect to a subgroup, whereas centralizer was with respect to an element or a subgroup. But even when we say subgroup, it basically boils down to with respect to each element in that subgroup. Whereas here normalizer is with respect to a subgroup. So Normalizer of subgroup H in G is equal to the set of elements of G, where G times H times G inverse is equal to H. That means they conjugate and the product remains in H. Let's look at the properties. If H is equal to the identity alone, that is a trivial subgroup, or H is equal to G, the entire group itself is the subgroup, then normalizer of H in G is equal to G. Normalizer of H in G is always a subgroup of G. Now, H is a subgroup of normalizer of H in G. Now, H is a normal subgroup of G if and only if normalizer of H in G is equal to G itself. That means every element of the group conjugates back into the subgroup. So for any A in G, if the subgroup H is generated by A, then the normalizer of A in G is equal to the set of elements of G, which when we take the conjugate, the result is in the subgroup generated by A. So centralizer of H in G is a subgroup of the normalizer of H in G. The index of normalizer of H in G is equal to the number of conjugates of H in G. Now let's look at an example. Same example of S3. So here, subgroups that we are taking is the trivial subgroup E, the subgroup generated by permutation 1, 2, subgroup generated by 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So here the normalizer of H is a set of group elements that conjugate the entire subgroup back into itself. So here for the identity alone, it will be S3. For 12, it is E, 1, 2. For the subgroup generated by permutation 1, 3, it is E, 1, 3. For the subgroup generated by 2, 3, it is E, 2, 3. Similarly, for 1, 2, 3 and 1, 3, 2 generated subgroups, it is the entire group. So, if you explore it a little bit, you will notice that the center of G is a subgroup of centralizer of H in G, which is in turn a subgroup of normalizer of H in G, and which is in turn a subgroup of G. Of course, in some situations, these two may be equal, the center and the centralizer. In some cases, these two may be equal. In some cases, these three may be equal. And with respect to some groups, all four of them may be equal to each other, depending on the groups that we choose. So that was centralizer and normalizer of a group. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.